Let's start talking about complex numbers today. And to start, we're going to solve this little equation, x squared equals 16. As you remember, we would solve this equation by taking the square root of both sides. The square root of x squared would be x, and the square root of 16 is either positive or negative 4, since 4 times 4 is 16, and negative 4 times negative 4 is 16. Solving the next equation in a similar manner, x squared equals 81. Well, the square root of x squared is x, and the square root of 81 is plus or minus 9. X squared equals 121. The square root of x squared is x, and the square root of 121 will be plus or minus 11. Here we have x squared equals negative 4. Well, the square root of x squared is x, but what's the square root of negative 4? 2 times 2 will equal 4, and negative 2 times negative 2 will equal 4. 2 times negative 2 would equal negative 4, but these aren't the same. This is where we end up needing to what happens here is there's no real solution. There's no real solution to this equation. And that's where we get into our next topic. The number I is defined to have the following property. I squared equals negative 1. Thus, I equals the square root of negative 1, and this is called the imaginary unit. As I said on the last slide, that equation had no real solution. Now we get into imaginary solutions. Numbers in the form a plus bi, where a and b are real numbers, are called complex numbers. A is the real part, the b or the bi is the imaginary part of this complex number. Equals 0, and b does not equal 0, then the imaginary number is pure because we would just have a bi part of the equation. It would be 0 plus bi. So that's a pure imaginary number, only an imaginary part. Pure imaginary number, or a non-real complex number, 7 plus 2i, since it has a imaginary part, is a non-real complex number. And a form a plus bi, or a plus ib, this is the standard form. We'll talk about why we sometimes write the I first as we go along. Writing as a complex number here, the first one we only have a real part, so it'll be the real part plus 0 times the I for the imaginary part. Here we need to change this into the I, so this could be the square root of negative 1 times the square root of 7. The real part is 5 minus I times the square root of 7. This is a case where we do put the I in front of the b. That is if we have a radical, because sometimes the radical, if we would write it 5 minus the square root of 7i, and we get sloppy about how long our line is for the square root, we would think we had I under the radical sign. So to avoid that, we put the I in front when we have a radical. We have the square root of negative 49, so that would be the square root of negative 1 times the square root of 49. Now the square root of 49 is 7, and square root of negative 1 is I. If we want standard form, we would have 0 plus 7. Now, equality of complex numbers. A plus bi equals c plus di only if a equals c and b equals d. So we can solve this equation for x and y. I'll show you how. This is the real part. and the real part of this complex number is negative 1. So x plus 2 equals negative 1, or x equals negative 3. Here we have the imaginary part of this complex number and the imaginary part. The only way these are equal is if this part equals this. So 2y minus 1 equals 5, 2y equals 6, and y equals 3. We're using the property that the only way complex numbers are equal is if the real parts are equal and the complex parts are equal. Now, if a is greater than 0, then the square root of negative I is, or negative a, is equals I times the square root of a. And when working with negative radicands, use that definition before any other rules for radicals. So if we took this as this is the square root of negative 4 times the square root of negative 9. That's the way it's written, and that's where we start. So we can start by multiplying. We get the 36, and the square root of 36 is 6. But if those radicals were written separately, as the square root of negative 4 times the square root of negative 9, it would be incorrect to go here first. We have to use this definition. So it's I times the square root of 4 times I times the square root of 9. So that square root of 4 is 2, square root of 9 is 3. So 2 times 3 is 6, and I times I is I squared. I squared, remember, equals negative 1. So this is 6 times negative 1, or it equals negative 6. Thus we found out that the square root of negative 4 times the square root of negative 9 does not equal the square root of the product of negative 4 times negative 9. Be careful. Using that, this will become I times the square root of 5 times I times the square root of 5. I times I is I squared, and the square root of 5 times the square root of 5 is 5. So we have we have I squared times negative 5, so that's negative 1 times 5, or negative 5, which is the answer we would expect when we multiplied the square root of a number times the square root of that same number. Going down here, it'll be I times the square root of 10 times I times the square root of 14. That will give me I squared times the square root of 140. Now the square root of 140 does have a perfect square factor. It's 4 times 35. So, and I is negative 1. So that would lead to negative 2, negative 1 times 2 times the square root of 35. And this one, we'll separate them first. I times the square root of 30 over I times the square root of 6. Now, it is legal to go ahead and do this right here. I and both the numerator and the denominator, they will cancel out. And we can make this one fraction and reduce it and have it be the square root of 5, since 6 goes into 35 times. Here we will have I times the square root of 45 times over the square root of 15. This real radical part will reduce. We'll still keep the I. And 15 goes into 45 3 times. So this will be I times the square root of 3.